Welcome to breadboarding. In the previous video we managed to test that our CGA video controller card that we've been making on breadboards was actually compatible with the original CGA cards and also exhibited the behaviour known as CGA Snow, which this high resolution test image here shows that whilst the CPU is actually updating the video RAM, then it interferes with the display here, and this sort of speckly bit here is what became known as video snow. The CGA comp utility we're using to test the CGA compatibility of the card also had this snow generation page, and this did lots of fast reads and writes to the video RAM to try and generate this sort of obvious interference here. And also the basic test samples that we looked at. So this city art example shows that there's a lot of interference here whilst the screen's been updating, and also the bouncing ball sample also shows the same interference. So this is video 59 in the Breadboard 8088 PC series, and this is the 14th video where we've been looking at building our CGA video controller, and in this video we're going to be looking at eliminating the CGA Snow. To try and explain what the cause of video snow is, I've modified some of the diagrams I've been using in earlier videos, and what we've got here basically is showing us the cathode ray tube controller, the control port that handles the various video modes, the clock PLD that handles a lot of the timing. The video RAM here is static RAM, which is quite fast, about 10 to 15 nanoseconds access time. The original CGA card had dynamic RAM, which had access time around 400 nanoseconds, so it's quite a bit slower. We then actually got the character latch, attribute latch, and the high resolution graphics latches over here, which take the data from the video RAM and send it to the video output logic. Our main address decoder here gives us a signal that says when the CPU is trying to access the CGA video RAM here. And as part of the design, I added this video data buffer here. So this is a fairly unusual chip, 74LS646, which is actually a bidirectional buffer, but it also includes latches on both sides of the A and B side, which makes it quite a flexible chip. Now the bits which are actually particularly involved in the CGA Snow, we've got two logic PLDs here which do a lot of the control logic for the CGA card, and when we're looking at the cathode ray tube controller accessing the video RAM and sending the video output, then we've got the CRTC address multiplexers for the upper address lines and the lower address lines. So when the CPU is not accessing the RAM in the CGA card, then CGA RAM will be 0. So I'm dealing here with positive logic. A lot of the chip enables are actually active low, but it makes it a lot easier to only be thinking about enabled equals 1 and disabled equals 0 here. So this is like the rules we use for the PLDs. So when the CPU is not accessing the video RAM, then the CRTC has full control of it. And what the video logic does is provide the video address output enable here, which enables these multiplexers. And it also provides the video RAM output enable so that the data can come out of here. And what happens then is the address lines generated by the cathode ray tube controller, so that's MA0 to MA12, and then there's the lower address bit here which toggles between 0 and 1, 0 for characters, 1 for attributes. So within an individual character cell, this will toggle between 0 and 1 during each character, and actually switches between the attribute byte and the character byte. What this allows us to do is the address information will come out of the cathode ray tube controller chip into the video RAM, and then allows us to feed the video data into initially the character latch. So the clock here generates a latch signal for the characters, and then a little bit later in the character cycle it will then do a later signal to do the attribute latch. And this is after the value here is changed from a 0 to 1. It will toggle on to the attribute byte and then will be written out to here. If we're in the graphics modes, then in fact in the high-res graphics mode we use a slightly different addressing here. So the raster address line 1 is actually used to toggle the RAM between two 8K blocks, where the RA1 toggles between even lines and odd lines. And you'll see down the bottom here that the video data then goes out to the high resolution graphics latch, In the 4-color mode, in fact, the colors are actually handled by the attribute latch. So this is what happens under normal circumstances when the video controller is scanning through all the video RAM and outputting it to the screen. So when the CPU comes to access the video RAM, this is what then happens. So we've got the same chips and things we're looking at here, only this time the address multiplexers for the CRTC are no longer going to be enabled. And you can see down here that the video data buffer is going to take part in this part of the process. So we've got our two logic PLDs for the CGA controller here, but we've also now got two additional latch stroke buffers. These are buffers for the main CPU address bus. So now when the CPU is accessing the video RAM here, then our CGA RAM enable will be true. And what this will do, at the moment, this is just hard coded to address latch enable is set to 1, which means it basically passes through. So in pass-through mode, any address here just gets passed straight through. And with the address output enable as well, and this just means that the CPU addresses can go straight through to the video RAM here. Because the video address output enables are disabled here, then these don't take any part in things. Because we're writing in this initial mode, we're writing data to the video RAM, so the control logic here will generate the write signal. It will actually disable the video output, RAM output, because we don't need to have the video RAM output whilst we're writing to it. And also what it will then do is this video data buffer is configured into pass-through mode. So the various control signals we have here, so some clock signals and select signals, are all set to basically just pass data straight through here or back out here on the basis of the direction. And then that means that the CPU data comes through here and then is able to update the video RAM. But whilst this is happening, we've also got the character latch and the attribute latches going on at the same time. And the trouble is that if those latches coincide with when we're reading or writing to the video RAM, then this is what causes the video snow. So these are the various video modes that we've got. So mode 0 is our 40 by 25 text. Mode 2 is high res text, so 80 by 25. The 40 by 25 was more for, say, TV output in the early days. Then our medium res graphics, 4-color graphics, is mode 4, and the high res 2-color graphics is mode 6. Now you'll see here that the character latch, attribute latch, and the latch used for the 2-color high resolution graphics is the same as the character latch. You can see here that the character latch down the bottom here, so this is some output from the logic analyzer. So we have the dot clock going along here, so this is the 25 megahertz dot clock in most of the modes. The 40 by 25 is half that speed. We then have the QA is dot clock divided by 2, divided by 4, and divided by 8. And QC is also happens to be the character clock. This is used to drive the CRTC to actually do each character cell on the screen. And you can see that during a full cycle here, where the values go from 0 up to 7, then back to 0, then the cycle periods here, the character latch is generally in cycle 0. The attribute latch is generally in cycle 4, although into some circumstances, in the 4-color mode, then in fact, for one reason or other, it actually is in cycle 7 there. But there does appear to be a period here between the character latch and the attribute latch here that we may be able to use for updating the video RAM, so this sort of quiet period here. So I've got some logic analyzer output here, and what I did is I added a anti-snow signal down here in this cycle 2. So you can see here that the character latch here is like cycle 1, cycle 2, cycle 7 here. And what this is showing is where we were writing to the video RAM here. So this is the write to the video RAM, and these two markers here show the gap between the end of the writing to the video RAM and when the snow clock cycle appears here. So you can see that the gap between writing to the RAM as it is at the moment and this cycle here can vary. In some cases here it's 70 nanoseconds, and down here when this write just misses the previous snow period, it can be actually this wider period, 590 nanoseconds. So One of the challenges here is that we've got the CPU clock which drives the memory read, memory write signals, but we've got the dot clock, the video clock, that drives all these other signals, and they will go in and out of phase, and so the gaps between the various transitions and things will vary from time to time. So this is in mode 0, 40 by 25, so this is actually a 12.5 megahertz dot clock. So you'll see the dot clock and QA are actually the same here in this particular case. The QD value is not actually shown in this particular one. Then in mode 2, this is our 80 by 25. You can see now that we've got the dot clock and QA are now actually different frequencies, and you can see that these gaps between the end of the write and the next snow period does vary, and we don't get there's gaps and things, so we don't always hit each snow period, doesn't have any activity. So we need to know when we have a write operation or a read operation is initiated, do we actually need to worry about doing anything during the next snow cycle? And in some cases we don't need to do anything. And then mode 4, this is the 4 color graphics mode. You'll see here that in fact the attribute shift register latch period is actually in clock cycle 7 here, just before we get to the character latch. And then in mode 6, this is the high resolution graphics mode. Again, this is fairly similar to the earlier ones. But you can still see that the way how these gaps and things are varying from each slide. If we picked a couple of extra few to the right, you'd see that these things would vary quite a bit. So it's likely that we're going to need to do some corrections and things at some point in time to allow for this variation. This is an example from the CGA Comp Snow generation. So this is just showing where we've got the writes, and there's also some reads going on here. And then this one is actually looking at the read specifically. So the video RAM writing here has got a much shorter clock period, where we've taken the memory write signal and narrowed it down to this smaller period. I hadn't done this at the point in time when I captured these logic analyzer outputs, but there would be a similar period narrowing down this memory read period in a similar sort of way. And what I was trying to show here really is that you can see here that our memory read period here may very well be coming up close to the snow clock cycle there. But in other cases, this one, it's missed it, so it's actually going to go up to the next one. And in fact, what you can also see here is the next one is actually falling outside of the memory read here. So when we'd actually be reading the value from the RAM and putting it into the buffers, would be outside the memory read cycle here. So in fact, what we might actually need to do is to extend this memory read by using wait states to actually the next value up here. So we're going to need to worry about on the reads on extending the read cycle time to actually cover the time when we are actually able to read the data from the RAM without interfering with the video display. So these 2 pages summarizing quite a bit of detail what we're going to be doing for the write. I'm not going to go through each line item in here, but fundamentally we're going to be making use of this anti-snow cycle 2, which is sort of the quiet cycles between the character and attribute latches. We're going to separate CPU writing to video RAM into 2 phases. The first phase will take the data and the address information into latches. In the second phase, we'll use the saved address and the saved data to actually write the data to the video RAM, and there's various things we're going to need to do to help support that. On the reads, we're going to again divide the reading into 2 phases. So in the first phase, we're going to latch the CPU requested address. And then in the second phase, when we get to the anti-snow cycle, where we can access the RAM without interfering with the video display, then we're going to read the RAM into the buffer and ensure that the CPU is then able to read the data at the end of the memory read cycle. But as we've seen previously, we may need to extend that memory read cycle with wait states. And in the 6809 project I did more than a year or so ago, when I got rid of the video snow here, I needed to modify the wait states and things for the CPU under some circumstances. It's worthwhile probably looking at the latch clocks, and in particular, a lot of these latches and things work on a rising edge. So the current chips that I've got for the address buffering are these 74LS573 chips. And you can see here that under normal circumstances, when latch enable at the moment is hard coded to high. So it basically means they just buffer the data going through. If they were to go low, then it would actually save what the current value is. And this is what the 8088 CPU does for some of the address lines which are multiplexed. However, we don't actually want to use that mode, because what we actually want to do is to latch the values on the rising clock signal. So the 574 latch will actually take the current input and save it on the rising clock edge there, and it will remain the saved value whilst it's on other values. So when it's low, or if it's at high, then we'll just get the saved values. It's only on the transition from low to high that we'll actually get the new value. And similarly, this 646 data buffer latch, the CAB and CBA clock signals again are rising clocks. So if we actually look at the sort of signals that we were looking at here, so the rising edge is this one here. So if we're low and then it goes high, then it's only on this transition where this one and this one are actually going to load data. If we actually wanted it to process the data at the end of the pulse, then in fact what we can do is invert the pulse, and so in actual fact the rising edge now becomes the end of the pulse. So if we get to anywhere where we say, oh hang on, we don't want it to occur at the beginning of the pulse, we want it to occur at the end, we may very well end up inverting it so that it's actually on the rising edge at the end there. So let's take a look at a possible way how to solve the snow situation. So we'll first take a look at when we're writing to the video RAM first of all. So again, we've got the same chips that we were looking at previously. And the things we need to change will be our CGA Logic 1 and 2 PLDs, programmable logic devices. We're going to need to add another one, and that's mainly because these can be clocked by different clocks, but the one PLD can only have one clock for all the various pins on it. And this one is being clocked by the CPU clock, and this one will need to be clocked differently. And we're also going to swap out the 573 chips here with the 574s, just because we need the edge triggering latching process here to actually get this to work. So now when our CGA RAM signal from the decoder is selected, so when it goes high, this is when the CPU is wanting to write to the video RAM. What now happens is there's a clock signal generated which actually clocks the data on the data bus here into the B register here. So it effectively takes the data from here and saves it on the B side here. That's what the clock AB means. The select AB and select BA being 1 means it's now using stored data rather than pass-through. So by stored data, what this means, it's using latched data now rather than just as a sort of bidirectional buffer. So then the clock signal for the two address latches then goes from low to high, clocking the address lines from the CPU into the latch. But note at the moment the output enable is not enabled for these, so at this point in time the CRTC still has full access to all of the video RAM, and outputting all the data going through here is going on in the background here. Then at one of the clock cycles, so cycle 2, the anti-snow cycle as I've called it here, what we do is identify that we've got some CPU activity, so either reading or writing to the video RAM, and we'll also save the direction that we need to do. And what this will then do is to trigger, during this sort of anti-snow cycle, it will trigger the address output enable. So this means now that these latches will become disabled. The saved address that we had in these latches here will now go to the video RAM. We'll then actually be telling the buffer here which direction we want to go, and we'll be enabling the outputs here. And that will then allow the data to come from the stored latch in the video buffer here and actually go into the video RAM. And the key thing there is that because this is being done during this anti-snow cycle 2, then there shouldn't be any snow appearing in the data feeds for either of these latches. So that's the writing to video RAM. The reading is ironically is a little bit more complicated. So we have the same basic part here again. So this time when we're actually selecting the RAM, we're still latching the addresses into the latches here, but the output enable is still disabled here. we've got our CPU activity and our direction, although the direction obviously is going to be reading this time. Now the issue here is that the CPU will be looking for the data from the video data buffer and will actually save the value as it is at the end of the memory read period. What's happening now, we're now clocking from B to A. So what we're going to be doing is taking the video data out of the RAM here and clocking it into the A register over here, so it's ready to actually send out to the CPU. And because we've done the address latch enable here, then the video RAM will have had the requested CPU address in here as well. And again, because this is being done during this anti-snow period, then none of these latches here will have been trying to get data from the video RAM at this point in time. And then what will happen is that the CPU will then read the data at the end of the memory read cycle from this buffer. The only issue is that, as we saw in some of the logic analyzer diagrams earlier, there are some circumstances where the standard memory read cycle may actually miss the data coming from here into here for anti-snow cycle. So we are going to need to add one or more wait states to certain memory reads so we don't miss any data. And that should again result in no snow. So the changes necessary for this have been quite complex. I'll just show you some of the updates to the KiCad diagram schematic that I've got here. So what I've needed to do is to modify the various CGA PLDs, control logic PLDs. So there's CGA logic 1, CGA logic 2. I had to rewire some of the connections around here, and we've added a CGA logic 3 as well down here. So most of the changes are within the connections here, here and here. Some of the connections from here down to these latches have now been replaced and now come from down here. So you can see here a number of the signals that were coming from here are now being removed and disabled. The values which are on here, which were originally connected to some of these here, some of these are now going down to this second PLD, or third PLD in fact down here. This is the logic 3, CGA logic 3. And because of the different clock timing requirements, so you can see that this PLD is clocked by the system clock. So that allows us to change the way how the memory read and memory write cycles are working. And this produces a signal coming out here called anti-snow, which is the cycle 2, and that actually provides the clock input to this other PLD. And because of that different clocking requirement, that's why you had to split this up into two PLDs here. And now this actually largely takes over the address latch output enables, the clocking of the address latches, the video address output enable from the CRTC. One of the clocks comes from this chip that goes to our 646, and the other clock comes from this chip. So basically between these two chips handles all the synchronization, all this stuff. So these rules are quite complex, and we've also got the CPU ready wait signal. So if we make this high, then the clock controller for the main processor will actually add wait states. So if we look up here, this will actually extend the memory read period by one or more clocks depending on the wait cycle there. So we're going to need to take out these two chips, replace them with the 574 equivalents, rewire a number of the connections around here, and put in another board for this PLD here. If we take a look at the PLD rules, so I also needed to fix a few things in the clock. So the clock, when I was looking at some of the logic analyzer outputs, there were a few things where the 40x25 mode was perhaps interfering a little bit more than it should have been doing. So some of the rules here have had a little bit more explicit sort of 40x25 mode in there. Also, I was finding that some of the test utilities that I was using were actually not using the BIOS mode setting routines, and so some of the mode flags were set in incompatible ways, that the card that I've developed here needs to have the high res flag set for everything other than 40x25 mode. So there's a few things to work around there. Then this is comparing version 4 and version 2 of the Logic 2 PLD. So this has probably had more of the changes here. So you can see here that there really have been quite a lot of changes doing here, because what I've effectively done is split some of these pins that were originally on here over to the third PLD. I'm not going to go through all the rules in here, they really are quite complicated to explain, but I think the diagrams largely explain what's going on, but there's a lot of different changes and things here, in particularly this anti-snow and the weight signals that we need for generating the weight states are all in here. Then the new PLD here, you can see that some of the inputs on the left hand side here are the same as what the other one had, but we've got these anti-snow, CPU activity and the CAB and the read address flags are coming from the other PLD, and these are all the outputs that then feed into the video RAM and all the various other latches and the 646. So all these things I have now programmed, and I've updated the chip labels. So chip labels are now got the new versions and things. It's already up to quite a bit of time, so I think we're up to about 20-25 minutes already. So what I'm going to do is to break the video here. So in the next video what we'll be doing is actually wiring in this new chip here and changing all of the wiring between these ones here, and then hopefully we'll then be able to test the video controller and see whether or not we've been able to eliminate the CGA Snow. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe, and if you can hit like as well, it just helps to make the videos available to more people. Thanks for watching.